This is lecture 21, example 1. And what we want to do here is start working with lookup tables and try to show that they're not too complicated. Certainly we need to use one in experiment 8, and this is why this is useful. So this is a little bit of a contrived example, but actually fairly straightforward, so let's do it. So the problem is to write a subroutine that calculates the parity of the value in x10. So x10 has a value in it. We're going to return the parity and what we're going to do is return a 1 in x10 or a 0 in x10. 1 for odd parity and 0 for even parity. So we've done this before, and this was our solution here. And what it does is it looks at those the LSB, and it does it 32 times. So essentially it masks the LSB and adds that to an accumulator. So here's your accumulator add here. Here it is copying that accumulated value into x10. I'm sorry, it's already in at x10, but what we're doing is masking everything but the LSB and putting that value in x10, and that was our answer. So this is the key here. Is there's an internal while loop in here that goes through this thing, worst case 32 times. Now it's worst case 32 times. That's how we set it up, because we set it based on this counter here. So it works great. It's a cool way to calculate parity. It's kind of like how humans do it, but we want to do it a little bit more differently. Now, the issue here is we want to use a lookup table. Now, this is the lookup table we're going to use right here. And so this lookup table has to do with nibbles. It looks at nibbles. So nibbles are 4 bits. So in a register, there are going to be 8 sets of 4 bits. And what I'm going to do is run each of those through the lookup table, each of those nibbles, and count how many ones there are. So what this table is showing is this value has 0 zeros. This is a 1. It has 1 bit that is set. This is 2. It has 1 bit that is set. This is 3. We'll put a 3 above it. It has 2 bits that are set. This is 4. It has 1 bit that's set. This is 5. It has 2 bits that are set. 6, blah, blah, blah. And 7 is this. It has 3 bits that are set. And I'll do the same thing for 8 through 15 as well. So this is a lookup table that is going to tell me how many bits are set in a nibble. And so the idea here is when I take a nibble, that nibble I'm going to use as an offset into this table. For example, if the nibble value is 7, I'm going to add 7 to this address, which is going to put me at the address of this piece of data right here, which is the data I'm interested in. So if the data was, I don't know, if the data was 15, we'll do 15. If the data was 15, I'm going to add 15 to this value, which is going to be pointing at the 4 here. Remember 4. This is 15. Okay, and yeah, that's it. Once again, I'm gonna use this lookup table to simplify my program out. So at this point, what I'm going to do, I think I'm going to write a flowchart for this. It's going to get kind of messy because I didn't save room for it, but let's see what we can do. Okay, so I'm going to say this is going to be checks parity. It's going to initialize some stuff, so stuff, but I'm also going to knit table. Notice that this is a piece, this is in the data segment. These are not instructions. I'm putting this in the data segment. But I will need to find the value of this address, and that's what this is going to do. You'll see that coming up. Next thing I need to do is I'm going to say that's done for initialization. And I'll say, am I done? And this is a yes. Okay, so if I'm done, what I'm going to do here is I'm just going to say mask LSB, and then I'm going to return. Okay, remember that the parity is going to be the LSB of this count. Okay, so when I'm not done, so this is a no, first thing I'm going to do is I'm going to mask data. This is the X10 data. I'm going to calculate the offset and I'll say do the lookup table. How's that? And then I'm going to get that value from the lookup table. I'm going to accumulate the value, and after I accumulate the value, I'm essentially done. So I essentially need to do some admin, which is loop admin and a shift, and then I can come back up here, and then I think I'm gonna call that done. I think this is gonna get kind of ugly, so I'm gonna go ahead and switch over to Venus. I like using Venus better. You can see it better, and we'll crank this thing out. Okay, so here we are in Venus land. This is the flowchart we came up with, so I'll be working off that flowchart. And so let's do this thing. I forgot what I named it. Parity sounds good enough. And I need to init some stuff. And so first thing, it's not overly apparent what I need to init, but think about it. It is going to be in a loop. I need to do something 8 times. So I'm going to move a value. Let's see. I got to get a value. I got to get 8 somewhere. So load immediate x20 looks good. 8. Okay, there's that. I know also I'm going to have a counter in here, and so the counter it just doesn't really matter which register I use for this. So this is going to be, let's say x15 x0. So that's, I might put some comments in here. Clear accumulator. Set. Here's my set iteration count. Okay, so the last thing, which is not apparent, actually there's something more important here. This is now the text segment. If I didn't call that the text segment, this wouldn't work. Okay, so I forgot about that, and I reminded me from the data segment. Okay, so the first thing I need to do is get the address of this thing, and this is going to be a base address of the lookup table. So this is going to be load address. I'm going to stick it in X30 for no apparent reason, and this is parval. I'm going to say store lut base address. Okay, so the value in X30 is actually the value of this byte right here. So this would be 1 plus that. So the issue is that I don't know what parval is. I have no idea what it is, but I know that value is in X30. So I don't need to know exactly what it is. I just need to know how to access it. And this is why, quite frankly, this is why I'm not really super good at these addresses, because I don't really work with them. I work with them through variables, and that's typically what most people do. And I think that's done with the initialization. So let's do this. This is going to be my main loop. Okay, so this one is it's a while loop, so I got to check the count. BEQ x20 x0. We'll say done. Jump if done. Okay, so there's that one. So the first thing I need to do is to mask the data in this thing. So I'm going to say I need to AND immediate x10, x10, x10. No, this is the result. So I'm going to store the results in x21 just for the heck of it, x10, and I'm ANDing it with 0xf. Now this is going to, I'll put this down here, mask the lower nibble. Okay, so at that point, if I mask the data, I'm going to have, let me come down here and get rid of this. Make that happy. Get that red line out of there. After this point, I need to calculate the offset, and so I guess there's a couple ways to do it. I'm going to say, what am I going to say? X21 now has the offset. X30 has the base register, and so I need to add those together, and I'm going to store the result somewhere. Add X22, and I'm adding X21 and X30. Okay, so this is calculate. I'll say it's a tough one. Okay, so X22 now is the address of the data that I'm interested in, and so once I have that value, I can accumulate it. And so this, oh, I need to go get it, huh? Load. So this is calculate off do LUT. Okay, so do LUT is load byte upper, and I'm going to say I'm just going to stick it back in X22 because I can. I could probably do this with less registers. X22 0 X22. Get data from GAU. We'll say from LUT. Okay, so X22 right here is the address, and that's the address plus the base register X30 plus the offset. I'm going to grab that data. I'm going to stick it in X22 just to save registers. That works, not a big deal. And then I'm good. I'm ready to add immediate and to my accumulator. My accumulator is an X15, X15, and this is X22. Okay, and it's not immediate. Okay. Okay, so that's the bulk of my algorithm, and I've done the LUT, I've accumulated the data. Now I'm at the admin step. Add min, and what do I need to do here? I need to, a couple things. I need to decrement the loop count, so that's add immediate x20 x20 minus 1. And then I need to massage the input data. So what I'm going to do is shift right logical immediate data is in x10, shift right x10, x10, and I'm shift it right 1 nibble. And I think I'm done. Jump, loop. Okay. Okay, and that's the main loop. And so at that point, what I need to do here is, what do I need to do? I need to mask the LSB. So I've got a count now. The count is in the accumulated value in x15, and what I want to do is mask that and store the result back in x10. So this is going to be, what is this going to be? This is an and immediate. I want to store it in x10, and this is going to be x, where is it? x15, 1. Okay, and there's the LSB masked, and at that point, I think I'm done. That's done. And then I can return. Okay, I think that's it. Yeah, I'll call that done. And so this is, I'll see if it works. I'm gonna say it works if it simulates. Okay, it looks like it simulates. I don't want to go through the simulation step. And the only thing is load byte. I am loading a byte, and I'm just call it done. Okay, so we need to go back over into the PowerPoint. So let's do that. I think I have a solution over there, but just in case, I'm going to copy this one. Okay, so here we are back in the land of PowerPoints, and we want to look at these solutions. So this right here is the old solution, and you know, you can see how you can count the instructions there. And here's the new solution. So obviously a little bit longer, and so that's the next question we'll get into. Is okay. So what we want to calculate is the worst case running times for both these algorithms, and so then discuss the advantages of both. Okay, so let's look at those. So this is the first one. So this is we're gonna count how many instructions it executes. So this is going to be 2. I always forget to turn the pointer on. This is going to be 2 plus 2 plus, let's see what we got here. This is a big loop here. This is 2, 2, 2, 2, 2, 2. So it's, and this is done 32 times. And this is going to be an extra 2, and there's a 2 and a 2. Okay, so that's going to be 2 plus 2, which is these two, plus 32 times 2, 4, 6, 8, 10, 32 times 12, plus 2, which is the loop coming through the last time, and this is plus 4, which is these down here. So 32 times 12 is, of course, I don't know. I guess I better do it. Oh, these are clock cycles. Okay, so we don't need to do that. Well, let's just do clock cycles since that's where we're going. So this requires 384 plus 4 plus 6. So this is going to be 394 total clock cycles for this algorithm. Okay, great. Okay, let's go check this one out. Okay, so this is going to be 2 plus 2 plus 2, and this is going to be our loop here. So this is going to be 2, 2, 2, 3, 3, 2, 2, 2, 2, and so this is going to be times 8. That's the key here. Times 8. And this is going to be a 2 more for this instruction, and this is going to be a 2 and plus a 2. Did we have a return the other one? Yes, we did. Okay, so that's going to be 2, 4, 6, 9, 11, 13, 15, 17. 8 times 17 is 8 times 7, 6, 5. 8 times 8, 136 instructions. So this is going to be 6 plus 136. So this 6 is right there. This is 136 from the loop, plus 2 for the branch, and plus 4. So this is going to be 146, 148. So total 148 instructions. Now this is compared to, I think, 394 for the other algorithm. So this one actually operates much faster. So the advantages are it operates faster. The disadvantages are it requires extra memory to store the table. And obviously the program itself is longer, so it takes a little bit of extra memory to store the program as well. So this is a classic trade-off. You, the programmer, have to decide which is the better way to do it. Once again, that issues the same result. One does it, about 40% of the time as the other one, but requires some extra storage resources on the microcontroller. And I think we're going to call that done for this problem.